Dimensionality reduction is a technique used in machine learning and data analysis to reduce the number of input variables or features in a data set while preserving the important information. The higher the dimensionality of a data set means the larger the number of features, causing problems like high computational complexity, curse of dimensionality reduction, and difficulty when visualizing and interpreting results or interpreting the data itself. Usually, the idea is to mitigate these issues by transforming your data into a lower dimensional space where each dimension represents a combination of the original features. There are two main approaches that you can use for dimensionality reduction. Feature selection, which includes methods like correlation analysis, forward and backward feature selection, which basically select a subset of the original features and discarding the redundant or irrelevant features. Feature extraction is another approach which includes methods like PCA, singular value decomposition, linear discriminant analysis, and t-SNE. The idea is to create new features by taking into consideration the linear or non-linear combinations of the original features. Dimensionality reduction helps you simplify models, reduce computational complexity, avoid the curse of dimensionality, reduce overfitting as a result of that, and speeding up the training process. It also helps you to improve the interpretability of your ML model and helps you visualize your dataset. So, what is PCA? At its core, PCA is a dimensionality reduction technique used to simplify complex datasets while retaining their essential features. Imagine you have a high-dimensional dataset with many variables. PCA helps us find the underlying structure of this data by transforming it into a new coordinate system where the variables are no longer correlated. So how does PCA achieve this? Well, it does so by identifying the principal components of the data, which are orthogonal vectors that capture the maximum variance in the original dataset. These principal components are essentially the directions along which the data varies the most. By retaining only the most significant principal components, we can effectively reduce the dimensionality of the data while minimizing the information loss. Let's break down the steps of PCA. You start off by standardizing the data, which is essential so that all variables have the same scale. Then you compute the covariance matrix of the standardized data, which would represent the relationships between different variables in the dataset. Next, we perform eigenvalue decomposition on the covariance matrix to obtain eigenvalues and eigenvectors. Eigenvalues represent the variance explained by each principal component, while eigenvectors represent the direction of these components. We select the principal components based on the eigenvalues and the top k eigenvectors corresponding to the largest eigenvalue to form the new feature space. Now, applications. Before we go to that, a commonly used method instead of eigenvalue decomposition of covariance matrix is also singular value decomposition of the training matrix. PCA can be used for dimensionality reduction, feature extraction, data visualization within finance, genetics, and many other fields. While it is a powerful tool, there are limitations. Basically, it assumes a linear assumption, and if this doesn't hold true, PCA is not going to give you meaningful results. You can use kernel PCA in that case, or other algorithms like UMAP or t-SNE. While PCA also simplifies the data, interpreting the principal components can be sometimes challenging, especially when dealing with complex datasets. And although it aims to retain as essential features of the data, there is inevitably some information lost during the dimensionality reduction process. Let us implement the PCA algorithm in Python. For that, you would need the scikit-learn library, particularly from decomposition, you need PCA, and from preprocessing, you need standard scale. We will be using the iris dataset. Once we load the dataset, see its features, we need to standardize the features and apply PCA to it by specifying the number of components. This value is a hyperparameter and can be found out using cross-validation. Next, you can display the explained variance ratio, which indicates the proportion of dataset's variance along the axis of each principal component. The first value, 72.729 or 72.9%, is the variance that lies along the first axis of the first principal component. 0.228 of is or 22.85% is the dataset's variance along the second principal component. We can visualize the data as shown. Finally, some notes. It is important that you select a good value for the number of components. It impacts the trade-off between dimensionality reduction and information preservation. For nonlinear dimensionality reduction, you can use kernel PCA, tsnE, or UMAP. If you have a large data set which does not fit into memory, you can also use incremental PCA, which basically does mini batch PCA. Finally, another term which is important to know is the reconstruction error, which is the difference between the original data and the reconstructed data, and it basically helps you quantify the information loss. In conclusion, PCA is a valuable technique for dimensionality reduction, feature extraction, and data visualization. By understanding its principles and applications, you can leverage PCA to gain insights from complex datasets in various domains. Thank you.